Hi everyone, we are Group 10 and our project is called Standing Wave Timer.
And I'm Yozong and I'm the leader of the team.
Hello, I'm Ding Xuehong, and I'm in charge of introducing the physical properties of the standing waves and the mathematical model of the standing waves.
I am Ujasan and I'm in charge of the Python models.
Hi, I'm Chen Yijia. I'm in charge of the circuit design.
Hello everyone, I'm Yozong. I'm going to talking about why we choose standing wave as our topic of our final project. In the beginning, we originally planned to make RC circuits to calculate time. However, we saw that there are many groups also make RC circuits. We wish our themes were a little bit more creative and also that there's very little information on using standing waves as clocks on the internet. So we decided to change our theme to standing waves. We use the time period of the standing wave oscillation to define our time. We hope to achieve the effect of the time period through the periodic line and dark changing between the photoresistor and the standing wave rope. Unfortunately, we found out that the shading effect of the rope over the photoresistor was not good. So we put the concept of the standing wave into circular motion, which is the projection of standing wave. In this part, Lin Xuehong will explain on our next part. And also we make a fence machine to cooperate with the photoresistor to generate period waves. And our machine is like this. And this is in the beginning we make a standing wave machine. And for our project for the timing we found a suitable IC to present the time conversion and then display the time with the 7 segment display to complete our topic. And that's why we chose the topic of making standing wave. And next part, Lin Xuehong will help us to explain the mathematical models and the physical principles.
I'm the first member to introduce our project, and I'm in charge of the physical properties and the mathematical terms of the standing waves. So let's look at our design. Our design contains a motor and a photoresistor, and is an electronic circuit. And our motor is connected with a cardboard. If we turn on the motor, it will trigger the rotation of the cardboard. And when the cardboard is rotating, it will periodically block the photoresistor from light and will thus generate periodic waves to measure time. And actually, we view every particles on the cardboard will follow the simple harmonic motion. So we are actually using the particles on the cardboard to stimulate the movement of the particles on the standing waves. So if we look at this figure, we know that the particles on the cardboard will rotate, and if we projected this motion to the horizontal plane where the photoresistor lies, we will find that it will move like a simple harmonic motion. And the important rationale behind our design is that every particle on the standing wave its acceleration will depend on its position. So it could be modeled as an ordinary ODE. So the capital Y denotes it's the particle's position, and the capital Y will equals to 2 times y0, which means the initial position of the particle, and times cosine omega t times sine kx. And we notice that the sine kx is actually a initial position term. So if we want to focus on only one particle, we will let this term to be a particular number, for example 1. So we get y will equals to 2 times y0 times cosine omega t. Next, we'll differentiate this expression 2 times, and we'll get its acceleration equals to y prime prime equals to negative 2 times the square of omega times y0 times cosine omega t. Notice that 2 times y0 and cosine omega t is actually the capital Y. So we could arrange this expression to get acceleration will equals to constant times y. So this is a typical expression for simple harmonic motion. Our particles on the cardboard will actually follow simple harmonic motion horizontally. So it will move periodically, and the blue ones is the photoresistor. It will switch between block stage and unplugged stage due to the movement of the particle, and it will thus cause the change of the resistance and the generation of periodic waves. Our periodic waves period actually depends on the omega of the cardboard. So the rotation speed of the cardboard does matters, and the change of the rotation speed could change the intervals of the times we measure. I'm going to introduce a little bit about our Python simulation, and I will focus on only one particle on the standing waves. So we set up a standing wave function, and we will get the particle movement on standing waves. Will you can see in this figure, as the times goes by, the position of the particle will swing between positive 10 and negative 10. And actually it will follow the simple harmonic motion, as we will see in the position and acceleration relationship. The acceleration of the particles depends on the position where the particle is, and it will be a straight line. So next, Jason will introduce more about our Python simulation.
Hello everyone, my name is Jason and I'm in charge of the Python demo for our final project. And I'll be going two things. The first is the basics of the standing wave, like basically how it looks like. And the second is the ideal simulation of our standing wave timer. Okay, so we'll go over to Python. The first thing we do is import numpy and matplotlib as usual. And then next is the parameters of the standing wave. And then this is the time, and then this is the amplitude, the period. And here we'll draw the three standing waves, or the three waves. First is the wave that's moving to the left, and then the next one is the wave that's moving in the opposite direction, so which is to the right. And finally we have the superposition of the two waves. And here we'll plot the waves. So the blue dotted wave, it's the wave that's going to the left, and then the orange wave is the one that's going to the right, and the green one represents the wave or the superposition of the two waves. Okay, next we'll go to the astable multivibrator, and here is the basic circuit of what the astable multivibrator is, and then this is an IC, and then here we have our input, which is done through C1, and then this is a triangular wave, and then the resulting output should be a square wave. Okay, and then first we'll do this using the capacitor as we have in the schematic that we showed. And first we import signal from SciPy, and here we have the VCC, and then the time, which this one is for if we directly input the triangular wave into the IC. And here we have the Vmax and Vmin of the output, or this basically limits the output, the voltage of the output wave. And here we have the capacitance and then the two values of the resistors. And then we doing simulation for 1 second. And here we have two functions which update the latch and update the value of the capacitor respectively. And here the capacitor is split into two parts, the charging and discharging, because it's not a constant value. And here we have our initial condition. The time is 0 and the value of capacitance is also 0. And here we'll do simulation of the circuit. This is with the capacitor as the input. And here we'll plot our results. So in the first graph, we see that the blue graph represents the value of a capacitor, and we see that it's a triangular wave, like as we've seen from the schematic. And then the output is denoted by the orange lines, which is a square wave that has a maximum value of 3.3 voltage or volts and 0.25 volts as a minimum value. And here the second graph is showing if we input the triangular wave directly without using a capacitor, and then the output wave is the same, but then the input is a triangular waveform that's generated by, say, a function generator. And as I said, this is an ideal simulation because, as we see, the output wave is a static square wave that's like continuous and periodic. However, in our actual demo, it's not like this case. Like I said, this is because this is ideal. So next we'll have 陈一佳同学 do an actual demonstration of our final project. Thank you.
Hi, I'm Chen Yijia. I'm going to introduce our circuit. At first, let's go to see the sending wave generator. You can see here is a motor carrying a fan, and the thing next to it is the variable resistor. You can change the frequency of the motor and also change the frequency of our standing wave. And we will put a photoresistor under the fan. When this resistor is covered by the fan, there is no incident light on it, so it will output a low voltage signal, and otherwise will output the high voltage signal. Okay, let's go to see the IC555. We will wire the photoresistor to this IC, and with this IC we can transfer our standing wave into a square wave. When the DIC receives a low voltage signal, it will transfer it into the high voltage signal, and otherwise will transfer into a low voltage signal. You can see in the These two pictures we shot in the laboratory. This is our standing wave, and we use this IC to transfer it into a square wave. Okay, let's go to see the third part of our circuit, the counting circuit. You can see the left-hand side is the IC74191. It is a binary counter. You can count the signal from the IC555. And the right-hand side is the IC7447. It is a decoder. You can decode a binary coded decimal to trigger the 7-segment display to function. Okay, this is the 7-segment display. You can see the picture in the middle is it, and the picture below it is the symbol that this IC to represent the number. You can see it can present the number from 0 to 15. Okay, let's go to see the summary of our circuit. You can see we create a standing wave and then transfer it to a square wave, and then count it, decode it, and then show it. Okay, this is the layout drawn by myself. Let's go to see the appearance of our clock. You can see here is a photoresistor, and then here is the IC555. You can transfer the wave into a square wave. And this is the counter IC, this is the decoder IC, and this is a 7-segment that show our time. Okay, let's go to see the demonstration. Okay, let's go to the next part, room for improvement. First and foremost, we think we should find a more stronger motor, because the motor we use now is too weak. It cannot rotate and carry the fan at a low angular velocity. If we get a stronger one, I think our time period can be more ideally. Second, we think we can add more counter circuit on it to show more details about the time, like to show the minutes of time, the hours of time. Okay, this is our room for improvement. Okay, this is the end of our project video. Thanks for watching. Bye bye.